section here is section 5.1. Here we're going through some stuff with the normal distribution curve. So we talked about this a little bit before, but we're getting more details into this now. So the first one here, we want to figure out which curve has the larger mean and which one has the larger standard deviation. So first of all, remember if you're talking about a normal distribution curve, it's symmetric, which means the mean, median, and mode are all in the middle of the graphs. So here, in other words, the mean for this graph would be right here, and the mean for this graph would be right here. So remember, if we're dealing with populations like we are here, our symbol for our mean is the one that looks kind of like a cursive U here. The symbol is called mu, mu. Mu is what that symbol is called. So here in this case, since the one on the right here has a larger mean because it's further to the right on the number line. So this one here has the larger mean. So once again, if you're on a number line here, both along the same scale, so this one would be larger on the right because it's further to the right on the number line. And then as far as standard deviation goes, remember your standard deviation is how spread out the data is. So here in this case, the one that's more spread out would be this graph here. So when the one with the larger standard deviation, remember standard deviation whenever you're dealing with populations here is this symbol. It's called sigma, is this symbol. And this one would have the larger standard deviation here. So your standard deviation is larger for this graph on the left because it's more spread out. So once again, our symbols here, we have our symbol for our mean, and the way that's pronounced is as mu, mu. It's the symbol for mean whenever you're dealing with population like we are here. And this one is for your standard deviation. I'm going to abbreviate standard deviation here, standard deviation. And once again, you're dealing with a population here. That's why we have sigma rather than s for standard deviation here. And this is called sigma, is how you say that symbol. These are some Greek symbols that are used to represent these terms. Just so that way, whenever you continue to see them, you remember what those mean as you're looking through your book. So example 2 here, we want to find our cumulative area that corresponds to a z-score of a 1.35. So what that really means for cumulative area, that also means that you're talking about the area to the left of that on your normal distribution curve. And I put a reminder here of where your chart is in your book, just like it states. It's at the end of the book, towards the back of the book, page A16 and 17 for your normal distribution table. That's where you can find the chart that you'll use for these types of problems involving z-scores. So that way you can find the area or your probabilities related to those. Area and probabilities here are used synonymously. They have the same type of meaning here. They're representing the same values. So here, remember, if you're talking about a z-score of 0, that would be in the center where the mean is. So that means a z-score that's positive is going to be over here somewhere. So here, for instance, z of 1.35 would be over on the right side here somewhere. Doesn't matter exactly where you're putting it. Just so you have a sketch of what's going on here. And then once again, if you're finding a cumulative area, you're finding the area to the left of that. So you're finding this area over here. And this area is the same thing as finding the probability of having a value over in this section. So we talked about that a little bit before whenever we talked about empirical rule earlier in the semester. This is also related to how they found those values from before. So to look this up, just like it has in the book, what you'll do is you'll go down to 1.3 on the left side where it has z, and then you'll have to go over to where it has the 0.05 along the top. So if you do so there, you should get 0.9115. So you'll You'll want to make sure you're double checking with your chart whenever you're looking those up. Once again, to look that up, along the left-hand side, you'll go down until you get to 1.3. And then to get this hundredths place, to get the 5 there, along the top, you'll have to go over until you get to the 0.05 column. So go down to 1.3 and then over till you get to the 0.05. And that'll represent this z-score of 1.35. So it separates between the tenths and the hundredths place. So that way they can get it all to fit on a one sheet of paper here, instead of having a long list there. So that would be for the area to the left of that value. For example 3 here, we now want to find the area to the right of it. So just like whenever we talked about probabilities before, how there has to be 100% underneath the entire curve. Here, if we're talking about it in terms of decimals here, that would mean 1 would be your area underneath the entire curve. So we can subtract from 1 the area that we had to the left. Because if we have 0.9115, that was over in this section for this area, for example 2, that would mean this area on the right side for example 3 would have to be 1 minus that. So it's 100% under the whole curve, or 100% as a decimal is the number 1. So then if we subtract those there, you get 0.0885. And these types of problems where you had one that was to the left of z equals 1.35 and the other one to the right, those are also what are called complements of each other. They're opposites. So all together, whenever you're talking about a complement, they should add up to 1 if they're covering everything underneath the entire curve. So something else to keep in mind there as well. Sometimes that can help shorten your calculations here. And then for this last one here, for example 4, we want to find the area in between these two z-scores. So if we're thinking of this on our normal curve, a negative z-score would be on the left side of our curve here somewhere. 2.15 is positive, it would be on the right hand side, and we're trying to find the area in between those two values, this shaded area in here. So we had negative 1.3. Remember, negative z-scores are less than your mean. So on the left side, positive are going to be on the right side above the mean. And the mean, once again, is in the center of the graph. So here, to find this, what we'll want to do is look up the areas corresponding to each of those z-scores. And then since we want the area in between them, we'll have to subtract the bigger area minus the smaller area. So remember, in your graph or in your table, whenever you're looking up your normal distribution table, your values that are positive are going to have larger areas because your table in the back of your book gives you all the cumulative areas, the areas to the left of that value. So that's something else to keep in mind there as well. So here, if we look up the 2.15, remember that means you're going to have to go down to 2.1 on the left side of your column, and then go over to the 0.05 along the top, and you'll want to write down that value there. So if you look that up, you should get 0.9842 there. 9842. If you go down to the 2.15 and then over to 0.05. Because the chart will give you the first two values, and then to look up that hundredths place, you have to look that up along the top and see where that row and column intersect. Reason I did that one first because I knew that one was going to have the larger value. And remember, anytime you're dealing with an area, remember these areas also represent probabilities. They should always be positive. They should always be between 0 and 1 if you're calculating them correctly. So if you accidentally do it backwards and you get a negative, Sure to remember the answer should always be positive for these types of problems. All right, for the other one there, for a z-score of negative 1.3, you go down to negative 1.3 in the chart. And you'll notice that the negative z-scores and positive z-scores are on two different pages. So this time go down to negative 1.3. And then you're going to have to go over to the 0, 0 column, the 0.00 column, because negative 1.3 is the same thing as negative 1.30. So if you go down to negative 1.3 and then over to 0.00 there, looks like here you should get 0.0968. And you do want to make sure that you're writing out all of the digits for these problems, all 4 digits. Otherwise, your values are going to be off. All of these values are very close to each other for the area, so make sure you're writing all of the digits down for these. So here then, if we subtract these two values, we get 0.8874. So then that represents what the area is in this region. Or in other words, we'd expect that there'd be about an 88.74% chance that one of the values from this distribution would be between this negative 1.3 z-score and a positive 2.15. So that's another way that these values are going to be used here as we continue through the chapter.